Good afternoon to all of you joining us today. My name is Namir Amsu. I'm a TDS Management Committee member. Timber Design Society Management Committee have recently agreed to a webinar series initiative in 2021 and just announced its very own monthly series with the first webinar happening today. Today's webinar is titled Reinforcement of Timber Members by Daniel Moroder. Stay tuned for future events happening in the forthcoming months. We welcome TDS, CSOC, and AGP members who joined us today. Thank you very much for doing so. A few housekeeping remarks. Daniel will talk for 40 to 45 minutes. Then we'll have questions and answers for around 15 minutes before the hour when everybody returns back to work. This presentation's recording, as Holly said, will be made available by Engineering New Zealand very soon. A little bit about Daniel. Daniel Moroder is a chartered structural engineer at PTL Structural Consultants, specialized in the design of timber buildings, originally from northern Italy. Daniel worked for several years in the timber industry before obtaining his PhD at the University of Canterbury. Working on multi-story timber buildings, and in 2015 Daniel returned to structural engineering consultancy with PTL, where he is continuing to pursue the boundaries of timber design industry. He is currently the president of the New Zealand Timber Design Society and co-editor of the Timber Design Society journal. Daniel is also involved in New Zealand and European timber design standards. Thank you very much once again, and please allow me to welcome Daniel, TDS President. Daniel.
Thank you, Namir, for the kind introduction, and welcome everyone to the first webinar of the Timber Design Society. I'm Daniel Moroder, structural engineer at PTL and president of the Timber Design Society. Now, I'm going to cover the topic of reinforcement of timber members, which together with the availability of mass timber products like CLT, LVL, and glulam, and the availability of new fastener systems like fully threaded screws has allowed us to design some very sophisticated new timber buildings, and has also allowed us to reinforce timber members. I will go into the presentation now, and I want to start with the major takeaway, being timber is a very forgiving material. So timber is very flexible. If you overload your beam, it will deflect before it breaks. Fasteners are typically ductile. So if you under-design your connection, it will normally deform before it breaks. Similarly, timber can plasticize when compressed. So it will deform, it will squeeze, but it will not break straight away. However, if you forget the main properties of timber, and one being that it has very low tensile perpendicular grain capacity, it could break and lead to a catastrophic collapse. So whenever you design timber buildings, please make sure that you check for tension perpendicular grain stresses, because they can lead to some quite brittle failures, which can lead to catastrophic collapse. So today's talk is about reinforcement of timber members, and is based on the NZ-BUD design guideline, which is available for free on the WPMA page, and is also linked on the Timber Design Society webpage. It is written in standard language, so in other words, it is written to comply and to be used along 1720.1, which will be our timber design standard in the near future. I happen to be the author of this guide, together with my co-author Tobias Smith, And I had support from the working group around Björn Stankovic, David Cardin, Gary Raftery, Manu Ciardalani, Felix Schallmeyer, and I also had support from Andy Van Hout as the technical manager of the NZ Wood guidelines. This guide provides all the recommendations and equations, which I'm gonna show a little bit today, and also some background information as well as examples which you can look after. Now, what we're going to cover today is why is it actually a problem? So we look at the basic properties of timber. And when is it a problem? What are the design scenarios where we really have to check for these perp to grain stresses? And what can we do about it? How can we fix it? What are the measures and how can we calculate for these stresses? So without going into great detail, timber can be idealized as parallel tubes. So the tubes in this case are the cell walls, which are making up the mechanical structure of the timber. These cell walls can be filled with water and other liquids, and that's where we have the moisture content in the timber itself. But structurally speaking, it is the cell walls which are doing most of the work. Now, if we load the cell walls, if you load the grain of the timber in the parallel direction, it can resist some quite high compression loads. Similarly, it can resist tension loads, again, parallel to grain. If we compress the timber perpendicular to grain, we're going to squash those tubes and it deforms. The timber will plasticize, but it will not break straight away. It will just deform in its size. However, if we try to pull those fibers apart, if we try to pull these cell walls and the idealized tubes apart, there's very little resistance and the timber will start splitting. And this is what we're going to talk about mainly today. Now, how often does this occur? It occurs regularly, most often seen in notches, so when you cut your beam close to a support. When you drill holes into your timber members, like for penetrations for services. When you have connections perpendicular to grain, they occur much more often than you actually think. We will look at when this might be the case. When we have multiple bolts in a row, so although I said that fasteners behave ductile, there could be brittle failure modes which we need to make sure they are prevented. Moment resisting connections for portal knees or multi-story portal frames. Bearing failures, as I said before, they're probably not as critical, but still deserve some attention. And we also could have shear failures. They're not as typical, but they could occur, and there is ways to reinforce for this as well. Glued-in rods also have a tendency to attract brittle failure modes when they're heavily loaded. And when we have variation of moisture content. And this is because timber is also hygroscopic material, so it will absorb and release moisture and therefore shrink and swell. If you have a steel blade which prevents this movement, it will likely crack the timber open because the steel is preventing the timber from moving. The timber has no choice then to actually crack. The other scenarios, which I'm not going to cover in here, which are curved beams and retrofit and repair, these are quite some specialist topics which I'm not covering neither here nor in the actual design guide from NZ Wood. So these are the typical design scenarios we're going to have to look at. And obviously the next question is, how can we prevent this? Now, one of the major breakthroughs in timber engineering were the invention of fully threaded screws. They have been around since probably 30 years in Europe, and they only have been imported in New Zealand since about 7 years. The major suppliers at the moment are Rotoblast, Spax and Worth, and there's other companies coming along with Schmidt, Eurotech, and also Black Fasteners have a range of fully threaded or engineered timber wood screws. So they're now commonly used in New Zealand, and most carpenters and builders are aware of them. Probably less familiar are threaded rods. They're similar to screws, but much longer and with a much bigger diameter, and they can be up to 3 meters long. So when you have very deep beams, you need to put a drill, and you can insert these threaded rods. They're just fixed by screwing them in. More traditionally in New Zealand, we can also use glued-in rods. They're working really well. However, they need a higher level of quality assurance because we need to make sure they are actually properly inserted. They need a controlled environment and a trained carpenter to insert them. whereas fully threaded screws can be installed very quickly without any major problem. We can also use glued-on panels. Typically, they're glued-on plywood panels. They require screw gluing to apply the pressure, and the guideline actually provides you some information on how to obtain this screw gluing. Less used and less recommended are nylon plates and toothed plates like the Tyler plates. They can be used to reinforce timber members, but as you can imagine, the connection to the timber is not as stiff and therefore don't provide this rigid connection, and they might only get activated once the crack is already quite open. So they're not as good as the other three types, so fully threaded screws, glued-on panels, and glued-in rods. What is the idea behind that? Now that we know that timber is not able to resist tensile perp-to-grain stresses, a bit like concrete, we can provide reinforcement with the use of screws, glued-in rods, and panels. They are providing the missing load path. Now, important to notice is that the reinforcement only limits the crack width and the propagation of the crack. It doesn't eliminate it. So you might still have some visual cracking occurring. This is very important to consider, as you might still get some onset of cracking, but it will be smaller. If you really want to prevent the crack from happening, then you can use glued-on plywood panels, but obviously you're creating another visual impact on your timber member. The idea also is that for most cases, you completely ignore the even small but still existing perp-to-grain tension capacity of the timber, and you rely only on the reinforcing members to do so. The exceptions being bearing reinforcing and shear reinforcing. I will now go through the notch beams with a bit more time and explain you the theory about it and how you can design the reinforcing, and we'll then go slightly bit faster with all other cases. As you can imagine, to cover all of this, it would take me several hours, and most of you are probably having a coffee or lunch right now, so I don't want to go too heavy on this. But I will cover the basic principles, and all the exact formulations and commentary is provided in the design guideline for you then to read and apply. So when you have notch beams, you actually force the shear force in the beam to go around this notch, which is a singularity, all the way to the support. By doing so, it creates stresses, mainly shear and tensile perp-to-grain stresses. In black, you see the theoretical curve, and in blue, you see the more realistic curve, which is based on observations and testing. So you can see that very close to the notch, there is a peak in tensile perp-to-grain forces. Now, if the timber is unable to resist them, and there is some quite strict rules in the standards of how to verify notches, most of the time you will fail the test. This means that there's a likelihood of the timber cracking. The idea is that you put fully threaded screws perpendicular to the crack line, which makes sure that these forces can be transferred from the bottom half to the upper half of the beam, and therefore guarantee the missing load path. So again, in a bit more detail, in black here you see the fully threaded screws installed, and you're making sure that the threaded part in the upper half of the crack and the lower half of the crack can transfer the load from one side to the other one. Instead of using fully threaded screws, you can use glued-on panels, and very similarly to before, you just need to make sure that the glued-on panel in the blue square and the glued-on panel on the green square can resist the load, and so can the plywood itself in its tensile capacity. By doing so, we're transferring the load from the lower half to the upper half, and we have guaranteed the load path again. There's obviously limitations of when you can reinforce. So there's a maximum distance or maximum depth as well. But there's also indications of how close or how far away reinforcement needs to be installed. Obviously, the closer to the singularity, the closer to the notch, the better. Which also means that if you use screws or glued-in rods, only the first line of screws or rods can be taken into consideration. This is because if these screws are not able to resist, it will go to the second line of screws, which are here shown in blue. And if they don't resist, it will go further and further, so you're creating a zip effect. So you can only rely on the first line of screws, otherwise you're not able to resist the actual forces. The same principle applies to most of the other scenarios where reinforcement is required. A quick note on CLT. Although CLT behaves a bit different than typical beams, if you notch CLT panels for a floor slab or roof slab, you still have to consider the notches, you still have to do your verification, and the disadvantage here being that the transverse layers don't contribute to the shear strength, and on top of the normal shear strength, you have to use the rolling shear strength, which is much lower. So also here, do your check, and if you fail your check, you better reinforce your CLT with fully threaded screws, which works very well. So now that we have quickly seen the problem and how we can solve it, obviously the next question is how can we determine the demand in our reinforcing? Now here a very simple equation which is based on rotational mechanics and equilibrium. It requires your shear demand in the beam and then a factor K51, which is based on the ratio between the effective depth and the full depth of the beam. It's that simple. The factor 1.3 considers that there is a peak in stress close to the notch, which increases this force a little bit. So your N star 90 value is your demand in your reinforcement. Once you have determined this one and you decide you're using screws, you can design the withdrawal strength. And we do that all the time with current design standards. If you're using fully threaded screws, you have to rely on manufacturer's data, mostly ETAs or Declaration of Performance, which provides you with the FAX value, which is, I pointed it here now, this factor here, which is based on the withdrawal capacity of your screw, multiplied it by your diameter and the effective length, and all relevant factors which are based on the material or the geometry itself. You then need to check your screw for L effective 1 and L effective 2 and making sure that both can resist the load. You also would have to check for the tensile strength of the screw, but it's typically not the governing factor. Finally, if you use partial threaded screws, for example for smaller beams or joists, you can also use those. You just need to make sure that you check both the withdrawal strength on the head side and the head pull through on the head side. Be aware when I speak about head pull through here, I'm talking about bearing strength and not about the head of the screw pulling through the whole timber member, because that would be too late to resist the crack opening. Finally, when you use glued-in rods, you have to check the withdrawal strength or glue bond, and you can do this based on Chapter 29 of the Timber Design Guide. And you also have to check for the tensile strength. Now, these equations can be found in relevant literature or in the guideline. When you use glued-on panels, you have to check the glue bond or the adhesion between the plywood panel or whatever panel you're using and the timber member. And there's values provided in the guide or also in the design standards. As mentioned before, you need to provide screws simply for applying pressure during the gluing process. You then also have to check for the tensile strength of the panel itself, and obviously only use the effective layers if you're using plywood. Now, this was a quick run through the notches and how you can determine the demand and how you can design for your reinforcing. I'm gonna pass on to the next topic, which are penetrations. Now, even more critical than notches, because notches normally you can prevent, you know them potentially during design already. Penetrations normally occur once you're on site and you have designed your 500D beam for 80–90% of use, and then the services guys come in and want to drill a 400 mil big hole through it. That obviously doesn't work with timber, and there's some very strict parameters you need to consider, and therefore that's something which normally should be coordinated long before beams go on site. Similar as before, if you cut out a piece of timber in the middle of your beam, you have not only shear forces, but also bending forces trying to go around your opening. And they create both, again, shear stresses and tensile perpendicular stresses. If you don't consider those, the timber might crack open as shown here on these sample specimens. You can have unreinforced penetrations, so you don't always need to reinforce them. However, there's some very strict geometric limitations, one of them being that your hole can only be 15% of the actual beam depth. You also have to consider the distance of the hole to the end grain, to the supports or any other force introduction, to the edges of the beam, and also in between multiple holes. All of them are quite restrictive. So if you satisfy these geometrical limitations, you then have to check the tensile per grain stresses in your beam. There's formulations for both sawn timber, glulam, and LVL in the guideline, and you can quickly check for those. Most of the time, you will have, you also have to check the section properties with its net geometry. So you have to take away the hole from your net section checks. Most of the time, you will have to rely on reinforced penetrations because your penetration probably will be more than 15%. So by using internal reinforcing like screws or glued-in rods, or by using plywood glued to the outer side of the beam, and by the way, that always needs to be symmetric, so on both sides, you can have hole sizes which are as big as 30 to 45% of the beam depth. There's a range because it depends on what type of reinforcing you're using and what type of material you're using. So the best results are for LVL beams with external reinforcing with plywood. You also have to follow other geometric limitations, but they're not as strict as for unreinforced penetrations. So similar as before, the idea is that you want to prevent the crack from opening and you want to transfer the forces from the lower half of the potential penetration, for the potential crack line to the upper half. So you need to check your reinforcing for an effective length 1 to the effective length 2, and you have to do it on both sides of your penetration. Now, because this crack can also occur on the other side, which is not shown here, it's really good practice to put the same type reinforcing on both sides of the penetration. Interesting to note that when you have a round penetration, the crack doesn't occur at the top, at the bottom, but it occurs at the position which is the intersection of the diagonal at 45 degrees through the round penetration. There is two formulations of how to determine the demand, one for sawn timber and glulam and one for LVL beams. I'm showing here quickly the demand for LVL beams. The principles are the same, there's just some slight differences in how these equations have been determined. These ones have been determined on mechanics, but also on empirical data from tests and finite element analysis. To determine the demand for penetrations, you have to consider both shear and moment. So although it is good practice to move your penetrations as far away as possible from the support, also in the center of the beam where there's no shear but there's potential moment, you have to consider a contribution from your moment demand. As you can see here in these two equations, and there's additional factors K62 and K63, which is a function of geometry and material, and the rest is all geometrical data which you have from your section. Once you have determined the two contributions, you can sum them up, and then you can design for your reinforcement. You also have to check the net section properties again for both moment and shear. This is a very simple exercise. However, on top of that, if you have rectangular openings, which you can imagine create a much more convoluted load path if you want, you also have to consider additional shear demand, which happens here at the end of the penetrations, shown here in red as T2, or tau 2. And the guideline provides additional shear checks with two additional factors to consider this increased demand at the edge of the penetration. Similarly, because of this rather long lever arm of the shear force traveling around this penetration, you have something like a frame behavior, which creates additional moment demand on either side of the penetration. So on top of your normal moment, you also have to consider the shear demand times half the length of the opening, which creates an additional moment demand, top and bottom of your opening. So based on all that, you can then design your penetrations and can make sure the beam works adequately. I'm moving on to the connections perpendicular to grain. As I said before, they might occur much often than you think. For example, the first case here, when you have secondary beams hanging to the main beam. If this beam would be on top, then there would be no problem. But because it's at the bottom, it tries to rip the timber of the main member apart. Similar when you have trusses. If the diagonal or the post is pulling upwards, you can try, or you're potentially trying to put the cord apart. This can also occur when you have hanging elements on a timber beam, for example, a steel member, or when you're pulling glued rods out of the timber beam. Similar principle as before, we need to make sure that this force is being hung up as high as possible into the beam, and you can do it by the addition of fully threaded screws. They can be either side of the connection, also in the middle of the connection, or you can glue on panels to resist this force. If you are able to apply the load at least 70% of the beam height, this is typically sufficient not to require any reinforcing. The new timber design standard actually has some very sophisticated equations to address this. If you fail the test, then you have to rely on reinforcement, and that's what we are looking at in here. Similar principle, as I said, there's a potential cracking line here at the first introduction of your force, and we just need to make sure that the force generated at the lower portion of this member can be hung up to the upper portion. And again, you just need to make sure that your reinforcing can resist the forces over the respective lengths, L effective 1 and L effective 2. Same principle applies for screws, glued in rods, or glued on panels. To determine the demand, the equations are quite similar to the notches. In fact, they're determined in a very similar fashion. Again, you have your demand, in this case, your tensile demand in the connection, multiplied by a factor, which in this case is the distance. The factor K56 is a function of alpha, which is the ratio between the distance to the loaded edge over the member depth itself. Once you have determined this demand, you can proceed designing your reinforcing, as we have seen for the cases before. Another case which requires attention are multiple bolts in a row. So we normally rely on ductile failure modes of our dowels and bolts, but if you have many of them in a line and you're pulling on them really hard, they're trying to push the timber member apart. It's just because of its geometry and the poor behavior of timber when loaded perp to grain. As you can see here, it tries to wedge out this whole part of timber, creating some sort of splitting and row shear failure. Especially if you want this to be ductile for a potential ductile element, then you need to make sure that this failure mode is prevented. You can again rely on the equations in the new timber design standard to do so. If you fail the test, you can also prevent this from happening by providing reinforcing. The idea here is again to make sure that this forces created by the timber trying to pull the timber apart is actually, there's actually a load path for them. This is a typical scenario with a slotted steel plate with 3 bolts or dowels, and by using fully threaded screws, you can make sure that these bolts don't have the ability to open up or to split the timber open. Important here is that you apply a screw behind each single bolt. If you have a single row of bolts, then you just have to make sure that the 2 halves are being connected accordingly. If you have more than one, you only have to connect the outer 2 halves together. The force components which would be created between the inner rows is cancelled out by each other. So you just need to make sure you have a screw going from one end, or one edge, to the other edge of the timber member, making sure that the splitting force is being taken by reinforcing. The demand is simple to calculate, can simply calculate with this equation here, which is about 30% of the characteristic capacity in shear per bolt per shear plane needs to be resisted by each single screw. So 1 screw per fastener per shear plane, as we have seen before. Based on that, you can design your fully threaded screw. Moment-resisting connections. They occur typically when you have barn structures or sheds, or when you have now multi-story timber buildings and you're relying on moment-resisting frames. Because of the nature of moments having different force components which are perpendicular to the radius of the center of the connection, you have potential resultant forces which try to create tensile perpendicular grain stresses in your timber, trying to open up the timber again, which is shown here in these two specimens. Now, this typically occurs when you have joints with more than one ring of dowels, and when I refer to dowels here, we're referring to large diameter dowels, so dowels or bolts. Typically, nails or screws it doesn't occur in this kind of scenarios, but the guideline gives you a bit of guidance on this as well. And typically, it also needs to be considered when you have ductile joints. So when you rely on these moment connections to be your ductile link in the structure. So you can either reduce the strength of your fasteners by about 15%, or you can rely on reinforcing. This is a typical example when you have a timber-to-timber connection. So we have, say, a double raft in the single column, and they're connected with a round pattern of bolts, can also be square. And as you can see here, because of the force distribution, there's a potential crack opening in both members at this outer corner of your connection. You can prevent this by using screws. Similarly, if you have this type of connection where you have a raft in the column connected with a gusset plate, that can be timber or can be steel. In this case, you have to do the same. It's just a bit more split up in terms of the rafter is reinforced up here and the column is reinforced down there. What is the demand in your outer corner? It is nothing else as the number of dowels in your outer ring divided by 12, which makes out about a sector of 30% of your circle, idealized circle if it's a square connection, times the demand of the fastener due to the moment demand. So based on this one, you know what is the force in your corner, and you can design your screw reinforcing accordingly. Remember that typically we have load reversals under seismic and wind actions. So in this case, you need to reinforce both outer corners, as shown in this typical case, where we have a double raft and a single column. So in this case, you have to put your reinforcing both at the top and at the bottom of your raft to make sure that both corners cannot split open. And similarly, you have to do the same at the column. You normally don't have to reinforce the lower part of your connection because it is further away from the end grain and has sufficient capacity to resist the tensile perpendicular grain forces. Again, this is something you really need to check if you rely on the ductile behavior of your connection, and I recommend you always apply reinforcing for that. Now moving on to reinforcing, which is not as critical because it is not as brittle. So you might have scenarios where your beam has very high bearing forces and it is too weak to resist the forces. This is a test specimen at the University of Canterbury, which has been heavily compromised by some quite high loads. The way to prevent or to improve that is to rely on fully threaded screws in compression this time. The idea is that you insert the screws and then cover them with a steel plate. I showed it here in a bit more detail. So the steel plate is down here and sits against the timber. So when you do your check, you're checking the bearing strength under the steel plate. So it's the bearing check of the timber. And then you also add the compression strength of your screws. And this is the first check you have to do at the outer edge of your beam. You then have to also check the bearing strength at the upper or at the end of the screws, considering you had a 45-degree stress spreading through the help of the compression screws. This means you have to do a simple secondary bearing strength check at this upper section of your bearing. What is a bit more critical here, that you have to determine the compression strength of your screws. And although the screw is embedded in timber, it still can undergo buckling. So there's some equations provided of how you can determine the buckling, the Euler buckling of screws embedded in timber. It requires some additional input parameters given by the manufacturer, but quite often the manufacturers of the screws provide you with the actual buckling strength of the screw based on the density of the timber itself, which makes the verification of reinforced bearing support quite straightforward. Again, there's more guidance in the NZ Wood guideline around that if you need to use this approach. I'm moving on to a quick summary on what we have seen so far. Unfortunately, I couldn't go into great detail of all the different cases because of limited time. But we have quickly seen of why this is happening, because timber only has good properties parallel to grain, but it doesn't have good properties perpendicular to grain. We've seen where this is typically happening. So notches, penetrations, connections perp to grain, as well as multiple fasteners in a row, moment-resisting connection, and compression perp to grain. We have seen that there's different ways to reinforce this, either with fully threaded screws, glued in rods, or glued on panels, and to a lesser extent, steel plates. And we've seen some design recommendations of how we can determine the demand. Now, the Timber Design Society has been trying to improve the uptake or to foster the uptake of timber in the built environment. And over the last 20, 30 years, we struggle a bit to convince designers and clients and developers to do so. But in the recent years, the focus has changed a bit because there's more and more timber buildings built out there, as these pictures here show. And our focus has changed, and we want to make sure that you're designing good timber buildings. And that's why we want to be more active now and reach out to you a bit more. And I want to finish my presentation with to showcase some of the activities we are doing as the Timber Design Society. So our mandate is to foster the uptake of timber as a construction material and to distribute the knowledge. We do so through our quarterly journal, which has articles about international research and also local research, of course, and we also showcase different projects. We also provide industry updates, and we recently introduced also technical notes. This is similar to this guideline, just addressing some of the missing items we have or we don't have covered in our timber standards. We will soon run a survey. It would be great if you could participate so that we can improve of how we publish our journal and what we are covering in there. As of today, we're also having webinars where we're covering design guidance like today. We're going to show sample buildings or we showcase local research. The webinars will be held each first or second Thursday of each month. And we're going to have webinars coming up about post and beam structures from Lisa Oliver from Holmes, the fire behavior of timber structures by Andy Buchanan, and Andrew Dunbar from Structex is telling us about his experience designing timber in Canada. For both the journal and the webinars, if you think you can or want to contribute with your knowledge or your project, please get in touch. It would be great to have you part of our journal or webinars. We also support students and young engineers with financial help. We have student scholarship for research projects, and we also try to send engineers to conferences. One of them was the Mass Timber Conference held last week, and we want to send engineers to the Woodworks Conference held later on in September in Rotorua. We had great success with the Christchurch Timber Forum 1 or 2 years ago, and we want to repeat this exercise now around the country. We want to organize site visits, factory visits, and seminars in the major centers of New Zealand, and we have a site visit at the Moroder Apartments on the 28th of April, and we're organizing site visits as well in Auckland. And again, if you have a project you want to showcase, please get in touch. We are happy to liaise with you and organize some networking events in your area so that you can exchange the knowledge and information with your peers. We also organize roadshows. We had a great successful one in 2019. We didn't want to organize one last year because of the pandemic. And we will make sure we're going to have another roadshow later on this year where we can inform you about the technical aspects of timber design. I hope you found this presentation interesting and you think that the Timber Design Society can be of use to you. So it would be great if you want to become a member, obviously, but we welcome everyone out there who is interested in timber. And I finished my presentation with a big thanks to my employer, PTL, for allowing me to spend some time on this aside from my free times in the evening. I also want to thank the TDS sponsor, Ixlam, FutureBuild, and MyTech, and obviously the Engineering New Zealand for the technical support we are getting all the time from them. Thank you very much. I hope you enjoyed this presentation, and if you have any questions, now is the moment to ask them. Thank you very much.
Thank you very much, Daniel. That was very comprehensive, thorough talk. Thank you very much for that. We have a long number of questions and we have sorted out according to the number of likes, those people who are interested to answer. First question, do we know when the new timber code is coming out?
This is a question we get very often. The truth is that there's still some small bits and pieces to be addressed, and the Timber Design Society has been very active on that. The Timber Design Society has reached out to some practitioners to do an industry-led review of certain aspects of the standard. And there's at least another workshop outstanding to finalize some of the aspects. And the aim is to have the standard published later on this year, is my understanding. It obviously requires some committee work and ballot, but we are at the last bits and pieces to get this standard available to you. Just one note around the standard. It is a new standard. However, it doesn't cover new aspects like CLT, glued-in rods, fully threaded screws, or anything about reinforcement of timber. So although we're getting a new standard, we already have to work outside that one, and that's why guidelines like the NZWOOD guidelines around reinforcement of timber are quite important as well.
Other question, the glued on panels, can the glue product achieve 50 years design life?
Well, certainly, if you use the same glues as being used for glulam or LVL, they can. But it is very important that any reinforcement with glued-on panels or glued-in rods is done by a trained person, or ideally a manufacturer themselves. But it's always a good idea to ask for the glue supply as well if the glue can guarantee the durability lifespan. I normally refer back to the timber manufacturers as they have the knowledge to do so, and they also have the best tools to do this reinforcing in the factory rather than on site.
Yeah. Is there any way to do reinforcement from one side only, as in most cases the other side will not be accessible?
Yes. As you can imagine, the force is across the whole section of the beam, so the crack will potentially initiate on one side, but will quickly propagate to the other side. Now, ideally, it is done on both sides, of course. If you cannot access the other side, then potentially it's better to reinforce internally, so with fully threaded screws. This can also be done on site, and it always can be done symmetrically because you can insert it in the center. If you cannot, then I would think do it with much caution and be conservative, because there's a likelihood that the crack will still occur on the side which is not accessible. So ideally, again, it should be considered before the beams are installed, so you have the ability to reinforce properly.
Now, thank you very much for one of our colleagues who provided a link to the design guide on WPMA website. Thank you very much for that. Now, how is the tension perpendicular to grain and reinforcement requirement captured in 3604?
Well, 3604 doesn't address that in great detail. However, there's allowance both for notches and for small openings. As far as I'm understanding, the notches are being verified with current design standards, so 3603. But it is very prohibitive, and you might be very quickly forced to choose a different solution. And what I've shown you today can be used to reinforce notches. I'm not fully aware how penetrations are being dealt with in 3604. But again, if you're outside those limits, I recommend you using this guidance here to design your penetration. Don't be scared to use a fully threaded screws. They're not expensive, they're quick to install, and they provide you a much better result. What I have not mentioned before, there's certain scenarios where I always recommend you reinforce. For example, a notched at the deck, so it is exposed to quite big moisture variations. So it's always a good idea that you reinforce a notch outside, even if the code says you don't necessarily require to do so.
Okay, we have another question. How is the tension? No, we have answered that. How should the durability of the glue be assessed for glued rods and glued panels?
As I said before, the durability is normally given by the glue supplier itself, or and especially when you have glued in rods, it should be done in a manufacturing plant, for example, Timberlab or Teclam or Nelson Pine or Hunter Laminates. They know best what glues work and what the durability is like. And if you do a glued-on panel on site, you need to make sure that the glue you're using and the manufacturer can guarantee the 50 years lifetime.
Okay, now another question. How do you represent combined bending moment and shear in your notch reinforcement of beam expression?
This is a very interesting question. So when you do the notch check, according to the New Zealand standards, there is allowance for both shear and moment. Whereas according to other international standards, this is not done directly, but it considers the distance of the notch to the support itself, and therefore indirectly considers the moment in your connection. For the reinforcing demand, when it has been determined through the mechanical properties and equilibrium, this equation automatically considers the moment demand at your support. However, when you have quite specific notches over a continuous beam, you're outside the normal theory, and you have to apply engineering judgment to address and determine the demand.
Thank you. One more question. Do we have a capacity calculation which will determine if the beam will require reinforcement or not?
For what scenario? Is there any more in the question?
That's all what I have on the screen.
Well, obviously, depending on what scenario you're looking at, the guidance provides different demands of. Sorry, I think I understand the question. For all the design scenarios I have discussed today, either the current standards or the guidance provides you with the capacity of the beam itself. So when you have a notched beam, for instance, you can use 3603 or the new standard 7020.1, which provides you with a check and tells you how much the beam can resist unreinforced. The New Zealand, the NZ guidance gives you a slightly different, more sophisticated equations to tell you if the beam can handle it. Similar to penetration, similar to perp to grain connections, there is always equations which let you assess the demand and the actual demand of the beam. If you cannot, if the beam cannot resist it, then you can, or you have to move to reinforcing and you can determine the demand. So yes, both the standard and the guidance provides you with the capacity of the beam with notches, openings, or perp-to-grain connections, and so on and so forth.
Thank you. This is an interesting question. Is reinforcement of penetrations in timber considered an alternative solution in the building code?
Yes. Everything I've shown today is at the moment considered an alternative solution. But don't be scared. Alternative solutions don't necessarily trigger peer review straight away. Now, for instance, LVL is not in 3603 and therefore would need to be considered an alternative solution. No council at the moment questions your design of LVL currently. So the aim of this guidance is as well that reinforcing of timber becomes a common approach and becomes industry standard. And although it might be an alternative solution until it will be cited in a future standard, it might need to be considered as an alternative solution. Also, the use of fully threaded screws or gluten rods is not covered in any design standard, and as such, always would be an alternative solution to the current legislation and building code. But don't be scared if you have one member which is based on alternative solution in your whole design in your calculation node.
Okay, short question. Presumably fully threaded screws mean coach screws?
I don't see a reason why coach screws cannot be used as long as you check for both the withdrawal strength on the thread side and the head pull through on the head side. It can still transfer the load. For instance, you could even use normal threaded rods with nuts and washers either side of the timber to resist your load, as long as you can guarantee the load path. The reason threaded rods with washers is not a good idea is because it doesn't allow or it doesn't consider the shrinking and swelling of the timber. And if your timber is shrinking a little bit, there will be a gap between your washer and the timber. But there's no reason why you couldn't use a coach screw, for instance.
Okay, now this is also another interesting question on fire. How will the crack affect the timber's performance in a fire, and how to prevent it fail prematurely in a fire as well? Yeah.
Yes. Obviously, we're going into some quite sophisticated question now because the likelihood of a crack opening and having a fire is obviously quite unlikely. Now, the cracks we're talking about, they're hairline cracks. They're very, very small. And research has shown that if there is a gap in a timber member which is less than, say, 5 millimeters, and this value can go up to 8 or 10, the fire doesn't create a big problem. It's not starting to char the timber in this crack itself. So it is my opinion that if you provide reinforcing, the crack will be small enough so that the fire doesn't create a big problem in your connection and you don't have to consider the crack as a potential charring area in your beam. So typically, I would think it is not a problem. However, what could happen, say you have a penetration and you have charring at the beam edges and also at the penetration itself, obviously your geometrical limitations become penalized, and you might have to consider this in your design as well. So I've had this, and I have decided to make the penetration a bit smaller than the maximum allowable diameter, so that when it chars, the section is still verified.
Okay. Another council-related question. Have there been any issues from the councils to accept capacity values for shear and tension and the timber for these screws?
Certainly they have when we started using them 5 to 7 years ago, but councils rely on engineers' judgment and obviously the ETAs. And I think most council engineers are now familiar with these products, with these screws, and accept them. But it is up to the engineer as well to make sure that he applies the guidance, the European technical approvals accordingly, and decides for them. Council could ask a question, but normally if you talk them through, they do accept this, considering they have been around for 30 years and are widely used around the world.
Okay, a question on penetrations. For round-shaped penetrations with holes size less than 30% to 45% of the beam depth, is the percentage diameter to depth? That's what I have. Is the percentage diameter to depth?
Yes.
What is the percentage of diameter to depth, possibly?
I don't remember exact values, and it depends on the timber used and what type of reinforcing, and obviously if it's round or square. But there's different ratios for round and for square holes. When we talk square holes, the diameter is essentially the height or the depth of the rectangular penetration. And if you look at the NZ Wood guideline, it provides you with all the different values, with the maximum being, I think, 45% of the beam depth.
This is another interesting connections question. Regarding bolted connections with bolts in line that can split the timber, are staggered bolt positions more cost effective?
You obviously can stagger the bolts, however, you still have to fulfill the minimum distance requirements between the bolts. I think the standards actually allow for that specifically. So it improves the behavior a little bit, but you still need to make sure that the splitting doesn't occur, and you still would have to check the brittle failure modes of your timber. And you will see once the standard is being made available, there's several failure modes to consider in such connection. I've only addressed the row shear failure, but there's also block shear failure. And this all needs to be considered. So once you start designing highly loaded, sophisticated connections with bolts, then it's good practice to look at them in a bit more detail. And when in doubt, apply some fully threaded screws as reinforcing. Typically, smaller diameter bolts are more efficient and more cost effective than fewer large diameter ones. And yes, I think staggering could help, but you still need to fulfill all the brittle failure modes equations.
Yeah. Now, we have a question. Where can we get the guidelines that you mentioned in the presentation?
I think it has been posted by someone in the chat here. You can also go on the Timber Design Society webpage, which is here on the slide, so www.timberdesign.org.nz, and there's a link to the WPMN guidelines. There's about 15 of those guidelines available. They're all free, and they cover everything from consenting timber structures to costing, fire design, post and beam, portal knee connections, construction, prefabrication, acoustic, and so on and so forth. So there's a wide range, and we hope, together with NZ Wood, WPMA, and other organizations, to deliver more of those guidelines.
Another question is, fire structural stability calculation is required where used in apartment buildings?
It's probably not related to this presentation, but post-fire stability is always to be considered. The building code requires that you do a check for gravity for your respective fire load combination vertically, and you also have to apply a horizontal load, which from memory is, I think, 2% of the gravity load needs to be applied horizontally, or a load of 0.5 kPa to your facade, to the elevation of the building. So this is always to be considered in your design.
Okay, the very last question. Are those penetrations less than or equal to 15% of the depth has also a testing specimen verification undertaken also that assures no reinforcement are required?
Well, typically when you have a penetration under 15%, I have to go a bit more depth here. Typically they say everything which is less than 50 millimeters in diameter doesn't need to be considered as a penetration. You only need to do a net section check. However, if you have a very small member, say 140 mil deep, and you have a 50 mil penetration, then this is already more than 15%. So generally speaking, when you have a penetration, you can use the equations to check if your beam without reinforcing can handle the forces. So essentially you check your stress, and then there's some capacity equations provided in the guideline which tells you how much the timber can resist on its own. If you fail this test, if you fail this verification, then you have to rely on reinforcing. Once you rely on reinforcing, you can make your penetration even bigger. On the other hand, you could have that your penetration is bigger than 15%, but the check would then say you don't need reinforcing. However, if you want more than 15%, you always need to reinforce. So this is how you need to look at that. So probably I should prepare a bit of a flow chart and show people how this can be done. And potentially I can add it in one of the technical notes of the Timber Design Journal so that people have a good understanding how to address penetrations in timber beams.
Just one last question.
Sure.
From Lisa, does the design guide cover increased capacity by catenary action? For example, screw reinforcement very close to the bolts, that the bolts hook.
Yeah, I understand the question. No, it doesn't address this behavior because it is being studied in Europe. There's guidance available out there, but it has not been used very often. I don't know exactly why, but I think it is a problem of installation because the screws need to be installed very close to the edge. If the screw is to the edge of the bolt, if the screw is installed too close, then you actually have you could damage the thread, making this additional catenary effect not working anymore. So there is obviously much more to cover when we talk reinforcing, which is available out there, and happy to take suggestions like this ones on board and publish technical notes in the near future. I also have to add, I haven't had time in the presentation today to talk about shear reinforcing or reinforcing when you have moisture-related shrinking and swelling of timber, or also when you have glued-in rods. So there is more information out there, and there's potential space for another webinar or other presentation on the topic in the near future.
Okay, thank you very much, Daniel. That was great talk today. And we have passed the hour now, and everybody is anxious to go back to work. And at the end, we would like to express our thanks and appreciation for your time to get this presentation done. And of course, we thank Enjoy New Zealand for their assistance to host this meeting. And the recording, as we mentioned at the beginning, will be ready within a week or so and will be sent to the members and those who attended the webinar today. Okay, thank you very much all, and we look forward to see you in the next TDS webinar. Have a great day. Bye-bye.
Bye-bye. Thank you, Namir. Thank you, everyone. Have a great day.